Hi, and welcome back to the Math Studio, where I've decided to install my lavalier mic on this three-dimensional model of the Cartesian coordinate system because I can't seem to remember to put it back on my body every time I stand up. So there it is. Anyway, I've had some people ask me, what's going on with the green screen? Was it damaged in the crash? No, it wasn't. That's the good news. The bad news is it has not yet been installed. It's actually over here against the wall. Let me show you. So there it is. I just have to put it up against the wall there. That blank space there is where I'm going to put it. So not to worry, we will be having some green screen fun soon. For now, though, we're stuck with this setup. So today we're going to be learning about vectors and specifically just some basic definitions, and so that we all are understanding vectors in the same way. I'm sure that some of you have already dealt with vectors quite a bit in your time in not calculus, but physics and other engineering courses. So like I said, this is mainly so that we can be all on the same page. So a vector is just a mathematical object that has both magnitude and direction. And we're going to represent it in our textbooks as well as in our PowerPoints and on various tests and so forth, either as boldface or with an arrow above the letter V. So think of it as an arrow, like you're shooting an arrow at something. That's a vector. So here's a couple of examples of vectors. You have vector V and vector U, and you have something moving from one point to the next. That's what vectors help us model. They help us model movement, something moving or something that is pushing against something. So forces also are good vectors. You have vector U over here, which starts at C and ends at D. The beginning of the vector is called the initial point, and the tip up there is the terminal point of the vector. The vectors that we're going to show you don't have a position, they just have magnitude and direction. So they just tell you what direction to go, they don't tell you where you are, which is kind of important. So when you combine vectors, you can combine them by adding them together, and think of orienteering, if you will, to think of this. Well, I don't know if that's a thing anymore. Back when I was a kid, they would send us out in the woods with a compass and tell us to go a certain number of paces due east, and then a certain number of paces north, and then so on, and eventually we'd find some treasure somewhere. I guess they do that nowadays, but they call it geocaching, and it's like a lazy man's version of orienteering. At any rate, that's what's going on here. Is you have two vectors. When you add them together, imagine moving along one of the vectors and then turning and moving along the other vector. So where you end up will be the sum of those two vectors. So that's what we mean um, in terms of the physical vectors themselves. So if you can imagine walking one direction and then turning and walking another direction, you could have achieved the same thing by just walking along the diagonal, if you will. Anyway, this definition is the definition from the book. Not all that complicated. The sum of the vectors is just what you get if you start at the initial point of U, end at the terminal point of V. And vector addition is commutative, which means you can go either U then V or V then U, you'll end up in the same place. So geometrically, there's what things look like. So scalar multiplication, also not all that complicated. If you have a vector and you multiply it by a number, that's what it means. Scalar is a number. Then you just end up with a vector that is that much longer. So if I multiply a vector by 2, then I have a vector that's twice as long as the original vector. Not all that complicated. Here's a few examples. I have vector v, and then 2v is the same direction as v, but it goes twice as long. 1/2 v just goes half as far. Negative v is just as long as v, but it goes the opposite direction. And then, of course, negative 1.5 v, opposite direction, and it's 1.5 times as long. This is somewhat important. Two non-zero vectors are parallel if they are scalar multiples of one another. And so, oh, well, that doesn't really, well, we'll have some practice for these things. Differences, you can do those in one of two ways. Probably the easiest way to think of this is to think of it in terms of u minus v is what you get is on the left-hand side here, you take vector u, and then you take vector negative v, so you have v pointing in the opposite direction, and then you just add those together, and you get u minus v is the same as u plus negative v. But another way, this is somewhat convenient to do, is that u minus v is also, turns out that geometrically it's the same as the vector that starts at the terminal point of v and ends at the terminal point of u. We're going to be breaking our vectors down into components that will correspond with your xy and xyz coordinate systems. And so when we talk about a component of a vector, what we mean is if we were to stick the initial point of the vector at the origin, where would the terminal point be? So in this first diagram, you have the vector A has the components A1, A2 because the terminal point of that vector is the point A1, A2. Similarly, in 3D, the vector A terminates at the point A1, A2, A3, and so that vector is going to be in component form just A1, A2, A3. Notice the kind of angle brackets that we have surrounding our vectors. That's to distinguish a vector from a point. So that the point on the graph A1, A2 has parentheses, and then the vector itself has angle brackets. So this vector A1, A2, it can be anywhere. It doesn't have to be at that point. So for example, here I have a whole bunch of vectors. They are all the same vector. I know they look like they're all different, but they're all the same vector. They all go across over 2 and up 3. So every one of these is the vector 3, 2. Now, let's just take a look at that upper right one there. Let me see. Can I make this? Nope. How about that? Ah, there. Now I can actually show you what I'm talking about here. Is the vector that begins at the point, is that 1, 3? Now it's too small for me to read from across the room, and ends at the point 4, 5. So that is the same as the vector that starts at the origin and ends at the point 3, 2. Now, one way to write a vector is that your vector A, so we'll call this A, is the terminal point minus the initial point. So in this case, A is going to be 4 minus 1 and 5 minus 3, which is the vector 3, 2. So this is just a convenient way to write vectors if you have a vector that you want to write in component form and you have the actual graph up there that you're going to be using. In 3 dimensions, you have a similar situation. If you have 2 points and you want to write down the vector that begins at one of the points and ends at the other, just do the difference of those 2 points, and that will be your vector. So let's go ahead and write down the vector that begins at 2, negative 3, 4, and ends at negative 2, 1, 1. So that I'm going to write as the vector AB. So we'll use that notation with an arrow above it. Let me make this a little bigger. So to write this vector down, we start with the vector B. Always start with the terminal point and subtract off the initial point. So for the x component, I start with negative 2 because that's the b, the x component of b, and then I subtract off the x value for point A. Let's do the same thing with the y values. The y value for b is 1, and I'm going to subtract off the y value for A, which is negative 3. Finally, we'll deal with the z values, 1 minus 4. Let me just clean this up. I get -4, whoa, sorry. Let's try that again. 1 minus -3 is, of course, +4, and then -3. And that's my vector. Okay, so magnitude, and then we'll call it, we'll close this video and start another one because we've gone a little bit long. Magnitude is just how long a particular vector is from initial point to terminal point. How far is it? So you're using the distance formula. That's all this is. It's just the distance formula. So I think that we're going to pause there, and then we will start up the next video and hopefully have some more examples.